from
Thank you. Okay, I hope you're already after the lunch and that you don't fall asleep. When I was asked to present something on roughness, Henrik didn't tell me anything about what kind of audience I would meet, and therefore I made it rather general. And now I see that there are a lot of experts on the subject here. So some people might be bored, and some people might learn something new. When I first started looking at rough walls, it was when I was a PhD student back in the 70s. And then there was a lot of activity on surface roughness on viscous drag on ships, because that was the time when the size of the tankers really exploded, and so the viscous drag started to become a very large fraction of the total drag on ships. At that time, the activity basically went on trying to correlate the surface geometry on the increase in drag that we see when we have a rough surface. And the main topic then was how do you describe the surface and what statistic parameters are important for the drag. Eventually that interest seemed to die out, maybe because it was too complicated. And there was a rather little activity until the 90s, when we started to look at what does the surface roughness do with the turbulent flow, or the turbulent structures. And again, we started something which was rather difficult, and I think we still think it's rather difficult. And maybe we don't have very many extra answers 20 years later than we had when this was a topic. But I'll talk a little bit about what we know about surface roughness effects. We all know that surface roughness increases the drag, and you can see that by looking at the Moody diagram, you may easily have an increase in drag by a factor of 5 or something. And we also see that if you increase the Reynolds number sufficiently high, basically all surfaces are rough. So it's a paradox perhaps that not more information or more research has been done on rough surfaces, which are from an engineering point of view much more important than the smooth wall, where we seem to have a lot of information about what happens. So there are still a lot of open questions. One of the essences in our recent turbulence research has been linked to Townsend's wall similarity hypothesis, where he suggested that once you get out away from the wall into the log layer, there's been so many eddy breakups and eddy turnovers that the turbulence doesn't really know how it was generated. But very close to the surface, there must be a region which is very much influenced about the actual geometry of the surface roughness. And you can easily imagine that it needs to be like that if you look at the perturbation around a cylinder that you insert into a flow. Then you will see that if you move away some 4 or 5 diameters, then the perturbation has dropped down to 1 or 2%. And so if you have a roughness which has a roughness height or length scale, okay, you would expect that, okay, the inner 5 or 6 K heights will be directly affected by the geometry, but when you get further away, the turbulence will be the same, whether the turbulence was generated by a smooth surface or a rough surface. And this has the implication that in the outer layer, when you suitably scale all your variables, that you will get the same plots for all quantities. I think the first one to really probe into this problem about the outer layer effect caused by the roughness was Tani, who in the late 80s published some analysis of a large number of experiments, and he found that systematically for rough surfaces there seemed to be a strength in the wake in the outer layer. And you can argue that it should be like that, or ought to be like that, because if you increase the skin friction by, say, a factor of 5 or something, then you increase the growth rate of the boundary layer, and therefore there should be a much higher entrainment from the outer flow into the boundary layer, and that should be undetectable in the strength of the wake. So there was also some observations about the stresses, the turbulence stresses, and there was a clear effect on the normal stress in the streamwise direction, very near the wall, but further out the observations were a bit more scattered. Some people said that there was a large effect also in the outer layer, and some people claimed that all the stresses would be the same in the rough and the smooth boundary layers. In the case of the channel flow, the information was more uniform, you could say, that there seemed to be much less effects in the outer layer than in the boundary layer. And that sounds perhaps plausible because, first of all, the wake strength as such in a channel flow is much smaller than in the case of a boundary layer. So if there is a change in the wake, it's much harder to detect it in the channel flow than in the boundary layer, where you have a wake which is about 3 or 4 times as strong. So it could be a question of observation, but it could be that there are real differences between boundary layers and flows in enclosed geometries. When you introduce surface roughness, you immediately add a number of problems or uncertainties into your analysis. And the first and most obvious is the question of where is your system origin. In the case of a smooth wall, there's no question about where the origin should be. It should be at the surface. But if I do a set of measurements on a rough surface, I may choose to set my origin at the top of the highest roughness elements, whereas someone else might say that no, it's the bottom, which is the correct location, and maybe the true origin should be somewhere in between. And in either case, you will have to find this origin, the origin that is the correct one for your description of the profile. So you will need to find this shift from your observation coordinate system to the physical coordinate system. This has effects on the wall, the logarithmic layer. In the case of the smooth wall, we know all the constants, basically. Some people may argue that we don't really know what kappa is, but kappa and B may be linked, and if you know one, then you should be fairly confident that you can determine the other one. So the only unknown in this equation is the friction velocity, which is very important because that's our major, our main scaling quantity. So we would like to determine that very accurately. When you introduce roughness on the wall, we have seen that you need to have a sort of shift in your physical coordinates to match the logarithmic layer. But you also need to change the additive constant because the effect of the roughness is basically to kill or partly kill the viscous sublayer. And the more you kill of the sublayer, the lower is your log law going to sit in the semi-logarithmic plot, and therefore you need to determine this shift as well. And the shift is then It's often called the roughness function because it measures the effect the roughness has on the mean velocity profile. So, if we want to scale our measurement in such a way, we have added two new variables. And since it's not so easy to measure the wall shear in the rough case as it is in the smooth case, although it's difficult in smooth case as well, we can't use established techniques from smooth walls like the oil technique that we saw in the previous session. It's very difficult to actually measure the shear stress. So most people tend to do some sort of a curve fitting, either to the log law as such, or you can add the rake and then do a matching to the full profile. So you have now three variables that you need to extract from the matching technique, and of course we can see that that reduces the accuracy of all of them compared to the smooth case. And the second question is, now that we have surface roughness, we have, instead of two length scales in the smooth wall case, in the smooth wall case we have the viscous length scale and the outer layer delta. In this case, you will have three scales. You will have the viscous scale, you will have the roughness scale, K, and you will have delta. So you need to match three regions, which means that you will have two matching points, and two matching points will be depending on K, the length of K with respect to the viscous length scale, and K with respect to the outer layer scale. And as far as I know, no one has actually attacked this problem and proven that we do have a log law. If we don't, then we do, of course, have a problem because we're trying to match our data to a log law, which we are not completely sure exists. I'd like to point out a statement in the review article that Rotta wrote in 1962 about boundary layers. And in his section on roughness, he says that the action of roughness can be interpreted as being equivalent to a reduction in the viscous sublayer. This suggests the following simple model for the representation of the mean profile. It is assumed that the universal law of the wall applies when the plane of reference is shifted beneath the surface by an amount epsilon. The plane moves with the velocity u, delta u, which will depend on epsilon, opposed to the main flow direction. If you say that, okay, we do have a log law, it seems plausible that you need to shift your origin some distance in order to match that log law. But if you do that because you want to kill the viscous sublayer. So you shift your origin into the wall, and then you need to let the wall move at an opposite velocity delta u. From a physical argument, I think this is a good description of what happens. And if you say that you know what the law should be in the smooth case, and you say that it's the same which applies in the rough case, you will see that this equation, whatever it looks like, is going to be changed into an equation that looks like this. So if you have the log law in the smooth case, this new law falls out automatically. So now it's not a question of constructing a new law, it's just applying the old smooth law to the rough case, and we get exactly the terms that we were looking for. I like that way of thinking. Okay, so we need to fit our data to this log law. And you need to find epsilon and you need to find delta u, and they will depend on your friction velocity. So you will see that there will be a lot of possible solutions. If you say that, okay, the slope needs to be the same as in the smooth case, then if you keep everything else constant, you will find that there will be only one shift, which gives you a collapse with the law. But if you let both epsilon and delta u and u tau be variables, you will see that you can get very many solutions here, which appear to be just as good as the other. So the uncertainty here is going to be rather high, and especially if you let kappa be a variable, then you have a fourth quantity which you can play around with. So it's really difficult to find a good match to the log law. Jackson proposed that if you let the origin be fixed at where the force actually acts on the reference elements, then you have removed one of the uncertainties or one of the variables, and that should improve the accuracy of the other ones. To me, it's a little bit difficult to understand why this location should be the correct value in the log law. I mean, it's going the opposite way. It's determining where the wall is, and then see if you have a velocity representation that actually fits that description. There's no, in my mind, no physical sound argument that says that where the force acts should be the shift that you need to do in the velocity profile. But it seems to have attracted a few followers. I could point out that if you look at the earlier data of, for example, the group in Melbourne by Perry, he had shifts epsilon, which shifted the reference point way into the fixed surface. And that means that epsilon is a sort of a fitting parameter more than a parameter which has a physical interpretation like this. And I like to use epsilon more as a fitting parameter. In the early works on rough surfaces, a lot of people used a statement by Hama, who did rough wall measurements back in 1954. And he said that, well, or going the wrong way, if Townsend's hypothesis applies, it must mean that the wake strength is the same for rough and smooth walls. But actually, Hama was the first one to say that. And so if you do that, then you will fix another parameter in your fitting procedure. So if you fix epsilon from here and you fix the wake strength from the smooth wall, then you only have u tau and then delta u as your parameter. But I'd like to keep the epsilon as a parameter and use that for the fitting of the data. But what now if the wake strength is not the same? Then you have more problems. My data, which goes back about 20 years, seems to support the finding of Tani that pi, this wake strength, is different on a rough surface than on a smooth surface. It could be that the high value which I got for my pi, which was about 0.7, was caused by background turbulence or some physical things in the wind tunnel, but I don't think so, since we got different pi's for smooth and rough walls. But if you have different pi's, you will see the difference in the velocity defect. And I plotted this sort of more or less standard function that you will have for a smooth wall with a pi as wake strength of about 0.55, and compare that to my measurements of a wake strength of about 0.7. So I get this curve. Now, it would be very simple for me to make my data match this one by changing the friction velocity. So you see that there's a link between what you get for pi and the friction velocity that you get from your curve. So when we presented this one, a lot of people seemed to object to our measurements, and it gave me a lot of sleepless nights, of course, because of all the criticism. But then people started to repeat measurements which had similar geometries, and some of them, like the very recent measurements of Schulz and Flack from America, seem to support our finding that at least there is a shift when you go from a smooth wall to a three-dimensional roughness to a two-dimensional roughness. Maybe there is an effect on the wake strength. And then very recently I've stolen this plot from Lee and Sung, who are preparing a paper these days, which shows DNS, and the dotted line is the 2D roughness. No, sorry, that's a smooth wall, and then we have the rough wall shifted slightly upwards, indicating that pi might be slightly higher also in this case. So at least we have some people who tend to give us support. If you say that, okay, this is my long wall and including a wake function, and you say that, okay, maybe our estimate of pi is wrong by some small fraction e, then if everything else is the same, if you think that you know where epsilon is, for example, by using Jackson's formula, and you think that you have a value for the shift, then if everything else is the same, then you will have a small change in your estimated friction velocity. And you can see what the ratio between the two uncertainties are going to be. And that's what I plotted in the next plot here. The ratio is going to be somewhere between 0.4 and 0.5. This is a ratio, and it depends on which part of the profile you're looking at. And normally when we do this matching, we will, if you just use the log law, you will be working in this region. If you do like I do and use the full profile, you will get something which is of the order of 40% uncertainty in the wall shear compared to the uncertainty you have in the wake strength. So if I say that, okay, my estimated pi was 0.7, but it should have been 0.55, then I find that, since I use the average across here, my estimate of u tau is off by about 13%. 13%, that means almost 30% when you look at the skin friction. And that's a very large uncertainty, and it's worrying, especially because u tau is our main scaling quantity. So if you have an error in u tau, you will have different shear stress profiles, you will have different stress profiles, and you will get a different shift in the log law. So I would have liked to measure the wall shear from first principles. And as I said, I can't use the oil technique because my surface is irregular. And so we designed this very, very simple surface balance. Here's our test surface. It's a section of our wind tunnel floor. And then under that, we have put a force measurement device, which is really simple. You go in the shop and you buy a small balance. You can buy it to weigh your post or other small quantities. We have a balance here which has a resolution of 1 milligram. And that gives us, compared to the force that we're measuring up here, it gives us a resolution of about 10 to the minus 4, a rather accurate measurement. So we measure the force on this one by transferring the force down onto the balance. And then I'll compare that to what we measure of shear stress in 3 different rough wall configurations. The first is a channel flow, where we know that we can calculate the shear stress distribution, and it should be linear, and it should scale to 1 at the wall, or extend to 1 at the wall. And you see our measurements, this time taking using lasers, in fact extracts or extends exactly to 1. And then we did the same type of measurements for a zero pressure gradient boundary layer. And again, you see that we have very good collapse with a theoretical curve. This one, which was obtained by integrating the momentum equation, and then the measurements that we have. And finally, we used the balance on a diffuser, which had a non-dimensional pressure coefficient of 6, and we got this nice linear shear stress distribution, which extracts back to the wall. When we compared the wall shear stress that we measured here, in the case of the channel flow, with the wall shear that you can calculate from the pressure gradient, we found that the total uncertainty, the uncertainty of the balance, including the uncertainty of measuring the pressure gradient, was slightly less than 3%. So we think that you can build this very accurate measuring device very simple. And if you do that, of course, you've taken away the major uncertainty, the most important uncertainty in your curve procedure. I'd like to show then some results for roughness effects from channel flows and boundary layers. This is a two-dimensional channel flow which we designed so that it should be very easy to define the geometry, and it should be possible to do the calculations both with the DNS and do experiments on the same geometry. And many of you have seen these results before. Here's our smooth wall simulation, DNS, and then the open symbols are from our smooth wall channel measurements. And then in the rough case, here's our rough wall measurements, and this is the rough wall simulation. And the reason why they don't collapse is because we couldn't run the wind tunnel at such a low velocity that we could match the Reynolds number. So this Reynolds number is about 50% higher than for the DNS. But when you plot the velocity defect, we see that in this case there is a small shift in the data, not very much, and you find the same shift in the DNS as we found in the experiments. But we would say that this effect now is rather small. When we do the boundary layer, we would perhaps expect to see larger effects of the surface roughness. We did two experiments, one which had a stainless steel mesh fixed to the floor, and this has more or less a three-dimensional random roughness pattern. So we would think that this would behave more or less like sand roughness. But then we added another experiment which had span-wise bars set at irregular intervals. And the idea of doing that was that we had seen from previous studies that if you use span-wise bars, you can get a roughness effect which is very, very large if you tune the diameter to the pitch of the roughness elements. And then the idea was that if you tune this so that you get the maximum roughness effect on the flow, and you let this continue for a very long distance, when you feed information at a particular wave number into the flow, maybe some of that information survives and extends out into the outer layer. And we set up this so that the shift in the log law should be the same, which means that it should have the same effect on the mean flow in the two cases. But in order to do that, we needed to change the Reynolds number slightly. So this is changed by a factor of 2.5 roughly. But it's still high, so we think that there are very little Reynolds number effects. And here is the data. I think that's spun out, I think. And here's our smooth wall measurements, and here are the two rough wall measurements, and you can see that they have the same shift. And when you plot this on a velocity defect form, you see that the wake shape is the same. So in both of these experiments, the wake strength was on the order of 0.7. That's somewhat higher than in the smooth case. Not much surprise there. And then we started to look at the expected effects on the turbulence statistics. And the first thing that we can agree on, I think, is that if you introduce obstacles in the flow, something is going to happen to the streamwise velocity components near the wall, and the most likely part of that energy, which is coming in the streamwise direction, is going to be diverted into the other two directions as the flow impacts on the obstructions. So we expect to see a reduction in the in the streamwise normal stress as we get close to the surface. What happens to the wall normal component is perhaps not as obvious. If you think about the origin being somewhere within the rough surface, then if you take a slice through that surface, you will see a lot of holes in the surface, and you may consider this perhaps as some sort of porous, a porous surface without any vertical net flow. And if that is the case, then you will expect the damping of the V squared to be less, and therefore the level of V squared should be higher near the wall. And at the same time, this impinging from the energy in the streamwise direction must be diverted partly into the vertical normal stress and the spanwise normal stress. So we would expect perhaps V squared and perhaps W squared to be increased as well. And if that's the case, then we would expect also to see something.
When you say V squared, it's V squared normalized
with
U tau squared.
Yes, sure. All the stresses, if you don't scale them, are increased. Yes, that's good. And then, of course, in the case of rough surfaces, you will have a lot of pressure drag. In fact, you will have, very quickly, you will have almost a total dominance of the pressure drag, and therefore you expect something to happen to the shear stress as you enter into the rough wall region. And this is what happens in the channel flow. I've got the expected reduction in U squared. Nothing much happens in the outer layer. In the wall normal stress, we do in fact get the opposite effect as we would expect, because you see that both the data, the measurement, smooth and rough, and the DNS, smooth and rough, indicate the same reduction in the V squared near the wall. And in fact, when we looked at the W squared, where we would expect part of this energy to go, we do also find a reduction in at least in the DNS. And you see that this reduction extends all the way to the center line. I have no explanation for why this should be more sensitive than the other two, but this seems to be more sensitive. And we get the reduction in the shear stress near the wall. In the outer layer, very little effect, because you have to end up with a linear distribution. Now for the boundary layer. As I said, when we produced our data, published our data for the span-wise rods, we got large effects and we got a large reaction to our data. And we were sort of alone about this observation for a long time. But then we have the data by Molino, Schulz, and Flack, which tended to show exactly the same, or in fact even larger effects, because we said that there should be very little effect on U squared in the outer layer, but they produce a significant increase from the smooth wall data to the rough wall data, also in the outer layer. And especially when you look at the wall normal stress, where we have our triangles, the inverted triangles here, showing significant, almost 20% increase in the outer layer. Schulz and Flack seem to reproduce the same with their black dots here. And the most peculiar looking thing is the shear stress profile, which our data go here, and so does Schulz and Flack. So the question is this strong effect now real? Could it be that it's due to the difficulty of obtaining the wall shear stress? Or could it be that the two-dimensional roughness acts differently, like we thought it would do when we designed our rough wall experiment? Or could it be that the outer layer effect is due to the differences in outer boundary conditions? Because in the channel flow we have a symmetry line at the center line, so therefore the outer boundary condition is more rigid than in the case of a boundary layer. And I think we need to perhaps have DNS to answer this. The problem with DNS is, of course, that you have problems reproducing the same high Reynolds numbers as we have in the experiments, and also producing a DNS for boundary layers seems to be an order of magnitude more difficult than doing it for channel flows. And I think perhaps, if I can be provocative and frank, I think that maybe a lot of the discussions and the conflicts that we have seen over the years entered when the DNS people came in and did the rough wall channel flows. Because as I said, we don't see this effect that you observed in the boundary, we don't see that in our DNS, so it must be wrong. But you can't compare apples and pears, and I think our measurements show this, that at least from an experimental point of view, are differences. And in comes more DNS people, and this time they do boundary layers. So let's see what they do. This is again data which I borrowed from Professor Sung. So he has a smooth wall plate where he lets a boundary layer grow, and then he starts by introducing roughness elements, the same type as we used in the channel. And you see, initially you get, this is the velocity field, this is the pressure field. Initially you get a large disturbance, a big perturbation to the flow, and then you start to get more regular patterns. And this computation of the domain, it extends much further downstream these days. But you see there's an inner layer which seems to grow from the roughness elements. And I don't know if he did this on purpose, but he seemed to be matching our shift in the log law very well. A shift here of almost 10, and ours is 11. This is my data. and this is the DNS smooth and rough. Again, small differences here perhaps, a little bit more differences in the experiments. And here is what happens as the flow meets the first roughness element. You start to get a large change in the skin friction, and you should observe that the skin friction goes negative. But also look at the scale here compared to the drag due to the pressure across the roughness elements, and you see that this is at least an order of magnitude higher. And then it turns into some sort of a regular pattern. Here's what the latest the latest DNS shows. Boundary thickness, which increases more or less linearly, and also the length scales delta star and theta. And if you have a constant skin friction coefficient, which you will expect to have if the flow was fully developed and the roughness elements are reasonably large, based on what you've seen on the Moody diagram, then all the length scales should increase linearly with distance, and the shape factor should be constant. So it's still not fully developed perhaps, but it's on its way towards a constant shape factor. And then the stresses. And I'm glad to say that the observations that they get from their DNS are at least qualitatively the same as we observed 20 years ago in our experiment. The increase in the stresses extends all the way through the boundary to the outer edge, about the same order of magnitude in the U squared, much lower in V squared than we got, but at least the same type of change. And also in the shear stress, they seem to have changed the profile significantly in the outer layers. So I think that we have evidence to say that in the boundary layers, there are outer layer effects from the surface roughness. I also stolen a figure from the vortex plots that they have given in their new paper. And you can see that there seems to be structural differences between the smooth wall, the two-dimensional roughness, and the three-dimensional roughness. And I think that they have found by doing two-point correlations that the inclination of the structures are different and steeper for the two-dimensional roughness than for the smooth wall and three-dimensional case. But I'm sure Professor Asung may answer any questions. I'll just skip the anisotropy, but there seems to be a tendency towards more isotropic flows when you introduce roughness, because you break up all the long streamwise structures and things become more three-dimensional. So, to conclude, obviously, as suggested by Townsend, there is a roughness layer near the wall where everything changes, but we've also seen that in the channel flow there is little effect, both in the DNS and in experiments in the outer layer. But in the boundary layer, we can argue how large the effects are, but they seem to be influenced by the rocks or the surface roughness. And I didn't show you, but there seems to be a significant effect on the third-order moments as well, which means that the turbulent diffusion has changed, and it must change if you change the stress profiles. So the open question, at least for me at the moment, is are the roughness effects dependent on the flow type, basically, or is it a question of geometry? And if I may suggest some experiments or investigations, I think that some people should look at D-type roughness in more detail than has been done before. Because if you have a boundary layer and it behaves like D-type roughness, which means that it's not the roughness scale as such which is important, but it's the thickness of the boundary layer that is important, then it must imply that there must be a very strong communication across the layer. And I think there's a lot of open questions there.
Time for questions.
Are you saying that for these effects are just a function of the entrainment, or there's nothing?
No, I suggested that, no, I don't suggest that that is a major effect, but I say that the strength of the wake, and you can argue that it could increase because of the entrainment.
And then all these, say, the things that GFR can that be a function of the thing? Have you tried putting all the things together in terms of the entrainment? Either the RDX or something like that?
No, I haven't looked at it, but it wouldn't increase at certain level, would it?
Oh, yeah, that.
Does it?
This one has a level.
Yes. Yeah. But if you introduce more entrainment, you introduce irrotational flow.
Yeah.
So it wouldn't
That's
increase.
why you increase speed, because you increase the pressure effect. Because you need pressure, so blood pressure will be because
Yeah.
pressure doesn't know.
Yeah. I haven't looked at it. But I agree.
You can't just go to the thing of the fucking
If you consider the outer flow structures evolved from neural structures, then you would expect the effect of surface roughness in the channel flow would perhaps be much less because the outer constructions are non-existent. So qualitatively, it does not look surprisingly so. I don't see any contradiction.
No, it just contradicts Townsend's hypothesis, which a lot of people simply believe is correct.
Are there measurements that you would categorize equally credible? The ones you have here where these things represent increase in terms of
No.
so what Fazli was just talking about right now could be explained by this way. Possible.
Yes, I think it's a good way to look at it. But as I said, I think that it's important perhaps to try to get away from the fitting procedure that experimentalists use and to try to sort out the main scaling parameter before we proceed.
Bill, if I can ask, when you talk about symmetry, essentially in the channel or height, you're imposing, you have a linear shear stress distribution and you can't get away from that.
Yes.
You're imposing that when the boundary laye's free to
Yes.
whatever it wants.
Yeah. We have to balance the pressure gradient.
Okay, we'll thank you for all again. And